Professor, and today I'm going to introduce the basics of thermodynamics to you. First things first, what is thermodynamics? Well, the short answer is that it's the science of energy. This brings another question. What is energy? We don't have a precise definition for energy, but we define it as ability to cause change or do work. Now, in this video, I'm going through these topics. I'm going to introduce the basics of systems and control volumes. Then I'm going to introduce system properties. And then we're going to discuss system state and state postulate. And finally, pressure and Pascal law. So let's begin with the definition of systems and control volumes. Consider a piston and cylinder full of air. This is a typical thermodynamic system. By definition, system is a bulk of matter or the defined region in space. So for example here, the air inside is our system. These red lines separating our system from the rest of the world are called boundaries. Anything outside the boundaries of our system is called the surroundings. A point you need to remember is that boundaries, for the sake of our thermodynamic analysis, have no mass and no thickness. This means they can't store energy. Systems can be grouped into two general categories: open systems and closed systems. A closed system has fixed amount of mass, whereas mass can flow in and out of an open system. A closed system is just called system for simplicity. A good example is a simple piston and cylinder full of some gas. By definition, no mass can cross the system boundaries. However, heat, work, and any sort of energy can cross these boundaries. The system boundaries can be stationary, like the cylinder walls, or moving, like the piston on top. Open systems, however, are usually called control volumes. They are typically a fixed region in space. Now consider this nozzle, for example. Fluid with mass flow rate in is entering from left and exits from right. These red lines again show the boundaries of our system, or control volume in this case. But take note that two of these boundaries, on the left and on the right, are actually imaginary. So boundaries don't need to be actual solid objects, they can be imaginary. Work, heat, and energy in general can cross the boundaries, no problem. We sometimes call the boundaries of a control volume control surfaces. Again, they have no mass and no thickness. Okay, now let's talk about the properties of a system. Any characteristics of a system is called a property. Let's revisit our piston and cylinder again. Let's assume 2 kilograms of air is trapped in a 1 meters cube cylinder, which by the way is a very large cylinder. 2 kilograms shows the amount of mass of our system. So it's a characteristic of our system, and so is a property. The volume is the same because it shows how much space is taken by our system. So both mass and volume are properties. Temperature and pressure are two other most common used properties in thermodynamic systems. Properties are divided into two main groups: intensive properties and extensive ones. Intensive properties are independent of the mass or size of the system, whereas extensive properties are actually dependent on the size and mass. A very easy way to distinguish which property is intensive or extensive is the example here. Assume you are measuring the pressure, volume, temperature, and mass of air in a tank. Then you go ahead and divide the tank into two sections using a thin membrane. Now, ask yourself this question: has the pressure and temperature in either side of this membrane changed? No, they are the same. How about mass and volume? Well, considering that air was homogeneous throughout the tank initially, then half of the mass of air ends up on either side. The volume of each side has also halved. So from this simple test, we conclude that pressure and temperature are intensive because they were independent of the size of our system, while volume and mass are extensive. Let's get familiar with a few more properties. We start with density in a specific volume. Density is the mass per unit volume of a system. It's an intensive property. You can check it with our previous example yourselves. Specific volume is the inverse of density, volume per unit mass of the system, and again, an intensive property. Please take note that we show specific volume with small letter v. There are two more less common forms of representing density: specific gravity and a specific weight. Specific gravity, we show it with capital letters Sg, is the ratio of your substance density to the density of pure water at 4 degrees Celsius, which is 1,000 kilograms per meters cubed. Specific gravity is mostly used to show the density of industrial grade oils. Specific weight, we show it with small Greek letter gamma and a subscript of S, is the density times gravitational acceleration g, which is 9.81 meters per square second in SI units, but for sake of simplicity, we usually take it as 10. We can now talk about the concept of state. Consider a system like the tank of air, like this tank of air that I'm drawing here, that is not subjected to any form of changes. In this case, we can measure or calculate every property of the system. These properties, in turn, describe the condition or state of the system. When, due to any sort of causes, the value of a system property changes to a new number, the system changes to a new state. We will see the importance of system state as we progress through the course. The state postulate is one of the most important tools in understanding thermodynamics. Its definition doesn't say much, but you'll see in future discussions how basic and important it is. The state postulate says that the state of a simple compressible system is completely specified by two independent intensive properties. First, what is a compressible system? A system that is not affected by any outside force fields, such as electric, magnetic, or gravitational, and so on, is a compressible system. For such systems, if we know the value of just two independent and intensive properties, we can find the state of the system and all other properties of that said system. If, however, our system is under influence of an outside force field, we need to know one additional property for every force field active on our system. For the sake of our thermodynamic analysis in this course, we assume all systems are compressible and gravitational effects, although present, are negligible on the state of our systems. Two properties that can always be used with this postulate are temperature and a specific volume. Please take note, not volume, but a specific volume. They are always independent. Another useful set of properties is temperature and pressure. However, we need to be careful. Temperature and pressure are independent when dealing with single-phase states, like when we are dealing with water or ice or steam or gas, single phase. When phase change happens, pressure and temperature are dependent, like when water is boiling or ice is melting. What we mean by that is we need the properties to be independent, meaning that we must be able to change the value of one without changing the other. But when water is boiling, temperature is a function of pressure. Let me give you an example. Now, at atmospheric pressure, the boiling temperature of water is always 100 degrees Celsius. But if we reduce the pressure to, say, 0.95 atmosphere, then the boiling temperature drops to about 97 degrees Celsius. So you can see that one is dependent on the other. So we cannot use them with this state postulate during phase change. Now let's define process and cycle. When a system goes from state A to B, we call it a process. When a system undergoes a number of processes and returns to the initial state A, we call the set of processes a cycle. Now, don't forget to put arrows on the processes so you know which direction it's going. Now, finally, we are going to talk about pressure. Pressure is defined as force per unit area, and in SI units is measured in pascals. 1 pascal is 1 Newton per meter square. There are 2 more units that represent pressure in SI. They are bar and atmosphere. 1 bar is 100 kilopascals, and 1 atmosphere is 101.325 kilopascals. In thermodynamics, the actual pressure of a system is called the absolute pressure. A very common form of reading pressure in application, however, is reading it relative to atmospheric pressure. We call this the gauge pressure. So P gauge is P absolute minus P atmosphere. Please take note that in thermodynamics, we are interested in absolute values of pressure only, but most devices read gauge pressure. So you need to convert them together, convert the gauge pressure to absolute pressure. A good example of gauge pressure is when we measure blood pressure. Blood pressure is usually measured in terms of millimeters of mercury, but if we convert it to pascals, we are looking at around 16 kilopascal max and 11 kilopascals min for blood pressure in an average human being. This is the pressure in a human body large arteries. We know that fluids only flow from high pressure locations to a lower pressure one. But if our inside pressure is 16 kilopascals and surrounding air is in an atmospheric pressure, which is 100 kilopascals, why do we bleed? Now, in order to answer that question, we should know that 16 kilopascals is actually the gauge pressure. So the actual pressure inside our arteries is around 116 kilopascals, which is bigger than 100, and so we bleed when cut. Now, congratulations, you now know another piece of useless information that you can impress your parents with. Now, moving on, how does pressure change with elevation inside a fluid? Consider a container full of a fluid like this. The blue diagram represents the variation of gauge pressure and shows a linear increase with respect to elevation. The red diagram, on the other hand, shows the absolute pressure and again shows a linear increase. We know from general physics or high school physics that the pressure increases as density times gravitational acceleration times the height of the column of the liquid. But why? Now, in order to answer that, consider a coordinate system like this inside the fluid where z is along the gravitational direction, x is normal to it, and y is normal to the page. We're going to take a fluid element and draw a free body diagram for it. Our element is delta x wide, delta z high, and unit in depth or y direction. It has a unit depth. The fluid is stationary and motionless, so the sum of forces in z direction is 0. Forces acting in z directions are pressure P1 and P2 acting on top and bottom sides respectively, and W, or the weight of the element. So sigma Fz is equal to 0. If we want to expand that, that is P2 times delta x times unit depth, which is 1, which we are going to assume is 1 and neglect from now on, minus P1 times delta x minus the weight, which is equal to 0. Weight is the density of the fluid times volume of the element, times g. Now here in the video, I forgot to write g initially, but I'll add it eventually. Now if we plug everything in the equation and cross delta x from both sides, we are left with delta p equals to rho g delta z. So that's where the equation comes from. Pascal's law is the immediate conclusion of this equation. Consider a container like this full of a clear fluid. If we take a horizontal line and take a few points on it, there is no change of elevation between any of the points on this line. So, based on the equation that we found, every point on this line, A, B, C, D, E, F, all of them have the same pressure. That is Pascal's law. every point on a horizontal line in a same liquid have the same pressure, only if you can connect them with a single continuous line. Now, if you can't connect your points with a continuous line, they don't necessarily have the same pressure. Let's assume that the circle area on the bottom is filled with a hashed liquid, with a different liquid that has a different density. Although points G and H are on the same horizontal line, they don't have the same pressure because you can't connect them with the single continuous line. But let's show that with equations too. Now, P of G is equal to P of D plus the weight of the column of the clear liquid between D and G. So P of G is P of D plus rho 1 GH2. P of H, on the other hand, is P of E plus the weight of the column of the hashed liquid between E and H. So P of H is P of E plus rho 2 GH2. You can see that although P of E and P of D are equal, the other terms are not. And so P of H is not equal to P of G. A very common example of Pascal's law in application is hydraulic jack. This is a simple representation of a hydraulic jack. We can put the heavy object on a relatively large platform and apply force on a relatively small platform on the other side of the system. Now, because pressure is equal between points 1 and 2, the fluid, usually oil, applies a much higher force on the heavy object, while the user applies a relatively small force on their side. The force applied by the fluid is easily calculated using this equation. Barometers are devices that were traditionally used to measure the atmospheric pressure. They are relatively simple in design. You have a cylinder that is drowned in a liquid upside down, usually with a vacuum space on top. In order to understand how it works, we need to clarify an important point. The pressure and the interface of two fluids is equal for each fluid. What I mean is that P of A is the same for air as well as the liquid in the container. If P of A of air was different than P of A of the liquid, we would see one of the fluids penetrating the other. Now that that's not happening, we know that the pressure at point A is the same for both fluids. Now, with that out of the way, we know from Pascal's law that P of A is equal to P of B. P of A is equal to the atmospheric pressure of air, while P of B is the weight of the fluid column above it. So, P of atmosphere is equal to rho GH. So when you hear the pressure is X millimeters of mercury or something like that, it means that the fluid of the barometer is mercury and the height of the column is X millimeters. Manometers are devices that use Pascal's law to measure the pressure of tanks, containers, and pipelines. This is a typical manometer reading the pressure of a gas tank. P1 is equal to P2 because of Pascal's law. P1, however, is actually the gas tank pressure, while P2 is equal to pressure at point 3 plus the column of liquid between 2 and 3. The U-tube is open on one side, so P3 is actually equal to atmospheric pressure. Plug in everything we know, we end up with P of gas is equal to P of atmosphere plus rho GH. This one is a little more complex example of a manometer reading the pressure drop in a pipe. Let's assume we have hashed fluid flowing through the pipe and another double hash fluid inside the U-tube. Based on Pascal's law, pressure at point A is equal to pressure at point B. Let's write both sides down. Pressure of A is P1 plus the column of hashed liquid. Pressure B is P2 plus the combined columns of hashed and double hashed liquids. If we play with the algebra, we end up with this equation. In the case that the flowing fluid is gas and its density is way smaller than the density of a liquid, then we can neglect it with respect to the density of the liquid and reduce the equation even further to P2 minus P1 is minus rho 2 GH. Thank you for sticking around to the end of this video. I'm going to put links to other videos, including a recitation video